In a heist movie, the crew always hides in, like, a van across the street, right?
Yeah, always the suspicious van.
Right. They spend weeks just snapping photos from a distance, memorizing guard patrols, and basically trying to figure out the security system without ever actually touching the building.
The classic casing the joint phase.
Exactly. But in network security, I mean, that phase only lasts so long. Eventually, the attackers, they have to stop hiding. They walk right up to the front desk, hand the security guard a clipboard, and legally ask for the bank's architectural blueprints.
Which is a terrifying thought, honestly.
It really is. And that's exactly what we're looking at today. Welcome to our deep dive. Today, we're opening up the official training playbook for certified ethical hackers. Specifically, we're looking at CEH v13 Module 04.
Module 4, which is all about enumeration.
Yes, enumeration. So for you listening, this is the critical phase where an attacker moves past that passive footprinting, the van across the street, and starts directly interrogating your target network. Okay, let's unpack this. We're going to explore how protocols that were, designed for trust and efficiency are weaponized to just map out an entire organization from the inside.
Yeah, it's the pivot from observation to active engagement. I mean, during the earlier footprinting phases, an attacker relies on OSINT, right? Public records, search engines, Shodan, that sort of thing.
Just to build a rough sketch.
Right, exactly. Just a sketch. But enumeration requires them to establish actual active connections with the target system. They are sending directed queries to the infrastructure to pull out highly specific data.
We're talking usernames, machine names, routing tables.
All of it. System architectures.
Right.
You are intentionally knocking on internal doors just to see what answers back.
And because you're actively sending packets and creating sessions, this is almost exclusively an intranet operation, right? Like you've already bypassed the outer perimeter defenses somehow.
Yes. Or you've gained a foothold on like a single compromised machine, and now you're surveying the landscape.
Okay, so once inside, the goal is just to find the weakest link to escalate privileges or move laterally. And the CEH module, it really heavily emphasizes exploiting remote inter-process communication shares, specifically the IPC $ share in Windows.
The infamous IPC share. Yeah, it's a hidden administrative share. And the thing is, it doesn't contain standard files or folders. It's actually a named pipe.
Unnamed pipe.
Yeah, it's designed exclusively to allow different programs and processes to communicate over the network.
Oh, I see. So an attacker scans the internal subnet, locates a machine with an exposed IPC share, and then attempts, well, what we traditionally call a null session, right?
In a null session.
They try to connect to that pipe without providing any username or password, just, hey, let me in.
And if the system is misconfigured to allow that null session, which happens, the attacker instantly gains a channel to query the system's registry. Yeah, they get the local security authority, the SAM database. It basically becomes the launch pad for a brute force attack.
So they aren't just like guessing passwords blindly against a web portal anymore?
No, not at all. They've actively mapped the share. They've confirmed the admin accounts actually exist, and now they're just hammering that specific named pipe to crack the credentials.
But to successfully interrogate these systems, the attacker has to speak the native language of the network layer, right?
Oh, absolutely. The module spends a lot of time detailing the foundational protocols, TCP and UDP.
Right, but not in a vacuum.
Mm-hmm.
It focuses on how their architectural differences present like distinct tactical advantages during this enumeration phase.
Exactly.
Because we know TCP relies on the three-way handshake, sequence numbers, acknowledgements to guarantee delivery. It's very polite.
Very structured.
Right. But UDP is connectionless. It just fires datagrams at the target with zero verification.
Right.
So I have to ask, if UDP is so unreliable and just drops data, why would network architects or hackers even bother with it when TCP is so organized?
Oh man, the exploitability of UDP during enumeration, it just cannot be overstated.
Really?
Yes. Because there is no formal handshake required to establish a session, UDP is incredibly fast.
Yeah.
I mean, you can blast thousands of queries across a subnet in seconds.
Just shotgunning the network.
Exactly. But more importantly, the connectionless state of UDP makes source IP spoofing trivial.
Oh, because it's not checking back with you.
Right. An attacker can craft a malicious request, forge the source IP to match a trusted internal server, and just fire it off. The target system receives it, assumes it came from a trusted peer, and sends the requested data right back to the attacker, or, uses it to reflect an attack.
Wow. Which brings us to DNS running by default on port 53. DNS utilizes UDP precisely for that speed, right?
Yes, exactly.
And when an attacker targets an internal DNS server, the CEH module flags the DNS zone transfer as the absolute jackpot.
The jackpot, yes. It relies on an AXFR request.
Right, which is legitimately used to replicate DNS records between primary and secondary servers just to keep them synchronized.
Right. But an attacker uses a tool like dig or nslookup, and they simply issue that AXFR request against the target's DNS server.
And what happens?
Well, if the administrator has failed to restrict zone transfers strictly to authorized IP addresses, which frankly happens surprisingly often, the DNS server just complies.
It just hands it over.
It dumps its entire database in plain text.
Oh, wow.
Yeah. We're talking about a complete map of the internal namespace. Every named host, every subzone, development servers, mail servers, and all their corresponding IP addresses.
That's insane. So the attacker doesn't even have to scan the subnet and risk triggering intrusion detection systems. They just asked the directory for the map, and it said, sure, here you go.
It's the equivalent of asking for the corporate phone book.
Unbelievable. Now, the module also highlights RPC, the Remote Procedure Call Protocol, operating on port 135. RPC acts as an endpoint mapper, right? It tells a client which specific port a requested service is currently listening on.
Yeah, and the vulnerability highlighted with RPC on port 135 is actually its susceptibility to denial of service conditions during this enumeration phase.
Okay, how does that work?
Well, an attacker can craft malformed messages directed at the RPC endpoint mapper. Because the service struggles to parse the garbage data, it can hang or just crash entirely.
But wait, a DOS isn't traditional enumeration, is it? I mean, crashing it doesn't give you information.
True, but attackers often use it strategically. If they can crash the primary RPC service, they might force the system to fail over to a secondary server.
One that maybe has weaker monitoring.
Exactly, or they just use the resulting system chaos as a smokescreen while they extract data somewhere else.
That's clever. Okay, then there's SMTP on TCP port 25, the protocol we use to route email. The CEH playbook points out that attackers connect directly to the mail server using like Telnet or Netcat.
Yeah, and then they exploit built-in administrative commands, specifically VRFY and EXPN.
Okay, break those down for us.
So when an attacker connects to an SMTP server, they can issue the VRFY command followed by a username. The server will respond with a specific status code. Usually it's a 250 for a valid user, or a 550 if the user doesn't exist.
So they just automate that?
Yep.
Yeah.
By scripting this, an attacker feeds a massive dictionary of potential usernames into the server. They just watch the status codes and systematically compile a validated list of legitimate corporate email addresses.
Just verifying who actually works there.
Right. But the EXPN command is even more damaging.
How so?
If they point EXPN at a mailing list, alias, say like all staff or exec team, the server literally expands the alias and returns the individual email addresses of every single person on that list.
You're kidding. Every single person.
Everyone.
Wow. And the downstream impact of that is severe. I mean, they aren't just pulling names for fun. They are using that validated list to launch highly targeted spear phishing campaigns.
Oh, absolutely.
Or they're feeding those exact usernames into a credential stuffing attack against the company's VPN portal.
It fundamentally arms the attacker for the next phase of the kill chain. The mail server is doing exactly what it was programmed to do, It's simply doing it for a hostile actor.
So once an attacker bypasses the perimeter and starts mapping these foundational services, their immediate next hurdle is navigating the internal hierarchy of the endpoints.
Right, getting down to the actual machines.
And in enterprise environments, that almost invariably means targeting Windows networks, which brings us to NetBIOS. Here's where it gets really interesting, I think.
It does. NetBIOS over TCP/IP is a legacy protocol, but it remains deeply embedded in enterprise environments for backward compatibility.
Right, for file and printer sharing mostly.
Exactly. When enumerating Windows systems, attackers are targeting UDP ports 137 and 138 and TCP port 139. Although I should mention, modern direct-hosted SMB traffic uses port 445.
The mechanics of how NetBIOS names function is just fascinating from an offensive perspective. It's a 16-character ASCII string, right?
Right.
The first 15 characters are the visible device name. So something like desktop HR04, but that 16th character is a hidden hex code appended to the end of the string.
Yeah, it acts as an invisible tag broadcasting the specific role of that machine.
It's like a secret code on a name tag that tells you exactly what their security clearance is.
That is a perfect way to put it. Using a built-in Windows command like nbtstat, ASA, followed by the target IP, or an nmap script like nbstat.sh, cat omps, the attacker pulls the remote machine's name table.
And they look closely at that 16th character.
Yes. If it returns 00, the machine is just registering a standard workstation hostname.
Okay, nothing special.
But if it returns 20, it indicates the service is running, meaning this machine is actively hosting shared resources.
Ooh, a target.
And if they see 1B, that is the holy grail. 1B identifies the machine as the domain master browser,
Meaning they found the primary domain controller?
effectively signaling to the attacker that they've found the keys to the kingdom, yes.
Wow. So NetBIOS essentially forces the machines to wear their security clearances on their sleeves.
Basically, yeah.
The module also heavily emphasizes the stool suite for this phase, particularly pexec and slogdon. Now, pexec is well known as a tool for executing command line processes remotely, allowing for lateral movement. But slogdon is particularly insidious in how it gathers intelligence.
It really is, because slogdon doesn't rely on querying the Windows event logs.
Which is good for the attacker because querying logs might trigger an alert in a SIEM platform, right?
Exactly. Instead, it directly interrogates the registry of the target machine. It scans the HKey user's registry key.
Okay, and what does that tell them?
Well, when a user logs into a Windows machine, their specific user profile hive is loaded right into that key. By remotely reading the loaded profiles in HKey users, slogdon can tell an attacker exactly who was actively logged into that specific endpoint at that exact moment.
Man, so they aren't just looking at active network sessions, they are literally reading the loaded registry hives to track administrators as they move around the network. Yes.
That has to be significantly harder for a defender to mask or spoof.
Oh, it's incredibly difficult. And if they pair that with a simple legacy command like netview computer name, ALL, they force the remote machine to dump a list of all its shared resources.
Just exposing those hidden administrative shares like the $C drive?
The underlying reality is that Windows systems are inherently deeply chatty. They are designed to constantly announce their presence and their capabilities to ensure seamless functionality for users.
Right, they want to be helpful.
Exactly. If administrators leave file and printer sharing enabled without stringent access controls, NetBIOS and SMB will gladly map out the endpoint architecture for anyone listening.
But wait, mapping endpoints only gives you half the picture. To understand the topology, attackers need the infrastructure layer, right? The routers, the switches, the firewalls holding it all together.
The plumbing.
The plumbing, exactly. And the CEH training points directly to SNMP for the Simple Network Management Protocol. That's running on UDP port 161 for manager requests and 162 for agent traps. SNMP is basically the nervous system of enterprise network monitoring. But its historical vulnerability lies in its authentication model.
How so?
SNMP uses what it calls community strings instead of traditional credentials. There's a read string for viewing configurations and a read-write string for modifying them.
Okay.
For decades, manufacturers shipped devices with the default read string set to the word public and the read-write string set to private.
Okay, let me push back on this, though. Are you telling me that the default password for enterprise-grade routers to hand over their data is literally the word public? We are talking about modern enterprise environments with zero-trust architectures and sophisticated EDR platforms. Are network administrators really leaving default SNMP public strings exposed in 2026? Wouldn't an active SLIMP walk across a subnet light up a SOC dashboard instantly?
What's fascinating here is you would really hope so, right? But the reality in the field is vastly different. While the core data center might be locked down tight, enterprises are riddled with legacy architecture. I'm talking IoT devices, deep internal switches, networked printers that were racked, stacked, and forgotten 5 years ago.
Oh, I see. The forgotten stuff.
Yeah. When a junior admin installs a new switch in a branch office, it is incredibly convenient if the centralized monitoring software can instantly pull it using the default public string. They intend to cycle the credentials later, of course, but technical debt builds, and it just gets missed.
And when an attacker finds that forgotten switch with an open UDP 161 port, they initiate an SNMP walk.
Let's dig into the mechanics of that. What exactly are they pulling?
They are pulling the MIB, the Management Information Base.
Okay.
The MIB is this massive hierarchical database structured like a tree. Every specific metric on that router CPU usage, port status, routing tables, is assigned an object identifier, or OID.
So an OID is essentially a numerical coordinate in that tree. Precisely. An attacker doesn't just ask for general data. They use tools like snapwalk or nmap's sample processes script to systematically iterate through those OIDs.
Now, the module mentions different protocol data units, or PDUs, used in these requests. They aren't just doing single GET requests anymore, are they?
No, attackers optimize the extraction. In SNMP version 2C and later, they utilize the getBulk PDU.
Get bulk. Sounds efficient.
It is. Instead of asking for one OID at a time, getBulk requests massive, contiguous blocks of data in a single query. And one of the highest value targets within the MIB is the ARP table.
Oh, wow.
Yeah. By pulling the ARP table, the attacker gets a list mapping every internal IP address to its corresponding physical MIC address.
So they aren't just seeing the logical network anymore. They are mapping the actual physical hardware layer of the target environment.
Exactly.
So they have the physical map via SNMP and the endpoint map via NetBIOS. The logical next step is identifying the users and their privileges. Active Directory is the obvious pivot here, which brings us to LDAP, the Lightweight Directory Access Protocol on port 389.
LDAP is the protocol that essentially acts as the phone book for Active Directory. It stores the entire organizational chart. Usernames, group memberships, departmental structures, contact information, all of it.
And the critical vulnerability during enumeration often stems from how LDAP handles authentication bindings, right? The CEH document outlines how attackers exploit anonymous binds.
Yes, anonymous binds are huge. Instead of providing valid domain credentials, the attacker configures their query to bind to the LDAP server anonymously. And if the server's access control lists are misconfigured to permit this, it's literally an open door.
And the execution is incredibly straightforward. The module highlights the use of Python scripts utilizing the Ldap3 library. An attacker writes a script establishing an anonymous connection, and then issues a search query using the parameter getinfo equals ldap3.al.
Which is such a dangerous parameter.
It effectively asks the server to recursively dump the entire directory tree, doesn't it?
It does. Without ever needing a password, the attacker downloads the entire corporate hierarchy.
That's wild.
They can parse this data to identify high-value targets, like members of the domain admins group, or map out the reporting structure of the finance department for targeted business email compromise attacks.
It's a complete exposure of the human element, but the module also focuses on a service that seems, honestly, entirely disconnected from users or files. NTP, the Network Time Protocol, on UDP port 123. NTP exists solely to keep server clocks synchronized to the millisecond. Why is an attacker enumerating a time server?
Because they aren't interested in the time. They're interested in the synchronization topology.
Oh, interesting.
Yeah, NTP clients have to constantly pull their designated NTP servers to maintain accuracy. Attackers utilize commands like NTP trace to follow the chain of time servers back to their source, or they use NTPDC to interact directly with the daemon.
It's like checking a synchronized bank vault clock, right? The attacker isn't there to steal the clock. They're using the clock's wiring to find out where all the other vaults are located.
That's a great analogy.
Yeah.
And the classic vulnerability here involves the monolith command.
Right. How does that work?
If we connect this to the bigger picture, if the NTP server supports the monolith command, an attacker can query it, and the server will respond with a beautifully formatted list of the last 600 IP addresses that requested the time.
600 IPs.
Yes. And if that NTP server happens to be positioned in the DMZ to sync with an external atomic clock, but is also servicing internal clients, well, that monolith response just handed the attacker a list of hidden internal IP addresses that are theoretically protected by the firewall.
So by tracing the electrical wiring of the clocks, they map the hidden vaults.
Exactly. And once they have those trusted internal IP addresses, they can leverage them against trust-based protocols. The module explicitly covers NFS here, the network file system, on TCP port 2049.
Right. NFS allows a system to mount a remote directory so it behaves like a local hard drive.
But the fatal flaw in NFS, specifically in versions prior to NFS v4, is its lack of robust user authentication. It relies almost entirely on host-based authentication. The NFS server maintains a file called /etc/exports, which defines exactly which client IP addresses are authorized to access and mount specific shared folders.
I see the synthesis here. If UDP spoofing is trivial because of the lack of a handshake, and NFS relies purely on IP addresses for authorization, the attacker just takes an internal IP address they just discovered from querying the NTP server, spoofs their source IP to match it, and sends a mount request to the NFS server.
Yes, and the NFS server looks at the incoming packet, checks the source IP against its exports file, sees a match, and happily grants full access to the shared directory.
Wow.
The attacker mounts the remote drive directly to their own machine. They didn't need a username. They didn't need to crack a password hash. They just needed to understand the interconnected trust relationships of the infrastructure.
This level of systemic vulnerability is profound, but, the final section of the CEH v13 enumeration module introduces a modern variable that radically alters the speed of all these operations: the integration of generative AI.
Ah, yes. Historically, the enumeration phase acted as a natural filter for attacker skill levels. To execute the attacks we just discussed, an operator needed deep technical proficiency.
Right, you had to memorize all the specific syntax flags for Nmap.
Exactly, and understand the complex hierarchical structure of SNMP OIDs to execute a proper SEMP walk, and know how to format LDAP search filters perfectly. It required a steep learning curve and just a lot of manual terminal work.
But the training document shows how that barrier is completely dissolving. Attackers are now utilizing AI models, specifically ChatGPT, directly within their workflows to automate the generation of these commands.
It's changing everything.
The module provides actual examples of prompts. An attacker simply inputs plain language. They say, generate the exact Nmap syntax to perform a full NetBIOS enumeration on the 10.0.0.024 subnet. And the AI instantly outputs the flawless executable command. So does this mean you don't even need to be a coding genius to map a network anymore? You can just ask a chatbot to be your hacker assistant.
Yeah, that's exactly what it means. But it goes far beyond just generating a single command. The AI is used for real-time error correction and dynamic attack chaining.
How so?
Well, if an attacker runs a Python script to perform an LD bind, and it throws a complex syntax error, they don't have to spend hours digging through Stack Overflow anymore. They just paste the error output back into the prompt, and the AI instantly analyzes the failure and provides the corrected syntax. It might even suggest a shift from an anonymous bind to an NTLM authenticated bind.
Does the AI ever hallucinate commands, though? Or suggest outdated flags that don't work?
It does, sure, but in an interactive terminal environment, that doesn't really slow the attacker down much. It becomes an iterative, guided process. The attacker feeds the hallucination failure back into the model, and the model corrects itself.
Wow.
It effectively turns a low-skilled script kiddie into an operator capable of navigating complex, protocol-specific syntax with the speed and accuracy of a seasoned penetration tester. It compresses the time required for the reconnaissance phase exponentially.
Which means network defenders have an incredibly narrow window to detect these probes before the attacker transitions from enumeration to active exploitation. We have covered a massive amount of technical ground today, analyzing CEH v13 Module 04.
It's a lot to take in.
It is. We've seen how attackers leverage the speed of UDP, the chattiness of NetBIOS, the default trust of SNMP, and the unauthenticated queries of LDLIF to map a network from the inside out. So what does this all mean for you listening?
The overarching lesson is that these protocols were fundamentally engineered for connectivity, reliability, and ease of administration. They were designed in an era where the internal network was assumed to be a high-trust environment.
Right.
The attacker isn't always breaking the system. In many of these enumeration techniques, they are simply asking the system to function exactly as it was designed.
Hackers don't always break in using complex zero-day exploits. Sometimes they just politely ask your network services for the keys, and the network happily obliges. The heist crew didn't need to break a window or pick a lock. They just found the right guard, asked the right question in the right language, and walked away with the blueprints. As we wrap up this deep dive, I want to leave you with a final thought to consider.
We've explored how seemingly benign queries like asking a server for the current time or polling a router for its uptime metrics can be weaponized to expose the intricate hidden topology of an organization.
Yeah.
When you analyze your own infrastructure, you have to look past the firewalls and the endpoint agents. Consider the legacy protocol silently operating in the background. As you sit at your desk today, what normal, perfectly functional internal services are running in your environment right now, quietly whispering your deepest infrastructural secrets to anyone who knows how to ask.
A critical question for any defender. Thank you for joining us on this deep dive into the mechanics of enumeration. Until next time.